Let's walk through practice set 6b, where we get some practice doing linear and logistic regression for numerical prediction and classification. So one thing you'll notice when you open up the RMD file for this activity is that I've added an additional note about having this warning equals false bit in the knitter options. Now this will become more important as we move on because in order to avoid excessive output, we're going to have to make sure to turn off warnings when we end up knitting. Otherwise, some of the routines that we fit can output hundreds of lines saying stuff about irrelevant warnings that we don't care about and that you don't want in your document. All right, so for this activity, we're going to load in the reg class library. And if you haven't already done so, you're going to need to install .packages caret. Now remember, you always want to do that down here in the console window because it won't knit with an install.packages command. And so you'll just type it with the package name in quotes. And you'll do the same thing for the proc package as well. So I'm going to load up these two libraries and we're going to get started. So this is our first foray into predictive analytics, and one thing that we know is that we don't necessarily care about how well our models are fitting the data on which the models are being fit, the training data. We're more interested in how well those models are going to be predicting brand new individuals the model hasn't seen before. And so the first step when doing predictive analytics is to take the data that we've collected and actually split it into two, the training data and then a separate holdout sample that we never look at again until we've selected a final model, and it serves as a sanity check to make sure that the model is actually generalizing about as well as what we expected. So question number 1 deals with the census data set, and in the census data set we want to be predicting the response rate, which is a percentage between 0 and 100. That lets us know what percentage of households actually mail back the census form that gets sent to them every 10 years. So since we're going to be doing predictive analytics and we want to develop a predictive model for response rate, the first step is splitting the data into training and holdout. Now I've said 50% training and 50% holdout. So let's go through the procedure for doing this. Now I'm going to borrow heavily from the notes that are associated with the Data Mining 1 set of slides here, and I'm going to go to the R code and worked examples. And what I'm going to do is I'm just going to find in the corresponding R file the slide title of the slides that have the useful code, because this code here pretty much just walks through the whole procedure. So I'm going to go over to that R file and I'm going to search for the name of that slide, which was Note on Examples, and I'll find it here. So all the examples in the set of slides dealt with the PIMA data set, so when I copy and paste this code, I'm just going to have to make a few changes. Alright, so to split the data into the training and the holdout sample, what I need to do is I need to randomly pick from the rows of the data that I'm working with at random. So I'm going to change PIMA here to census. And I'm also going to change this 0.75. This example in the notes was specifically for making 75% training, 25% holdout. And in this case, I want a 50-50 split. So I'm going to run this line that is starting out with set.seed so that we all get the same random assignment of the data into training and holdout. That's important so that we can all grade your work so I know what answers you're going to get. And once we've determined what the vector train rows is going to be, if I just print that out to the screen, it's a random assortment of row numbers. That's going to tell me what goes into the training and what goes into the holdout. So what I'm going to do is I'm going to define the training set as the census data set, but only the row numbers that appeared in train rows, and holdout is going to be everything but. That's why that minus sign is in front of there. So we'll define the training and the holdout sample, and then I say, all right, let's verify that we get these results. Yes, it looks like we've done this split correctly. We're reproducing the expected training holdout split. All right, the next step when doing predictive analytics is to tell R how we want to estimate the generalization error. Now, our standard is repeated k-fold cross-validation, so we need to set that up. We need to define an object called fit control that lets it know that, hey, we want this number of repeats of this number of k for k-fold cross-validation. And in this case, I ask you to estimate the generalization error with 8 repeats of 6-fold cross-validation. So let's look to see how this is done. I'm going to go back into the R code associated with the slides, and here's the example that lets us know how we set up cross-validation depending on what we're predicting and exactly how we want to be predicting this. So depending on if we're doing regression, numerical response, we're going to set it up this way. For classification, the syntax is a little bit different. There are a few extra arguments. So in this case, what I want is I want some repeats of k-fold cross-validation. And so I'm going to select this line and just copy it into here. So I want method equals repeated k-fold cross-validation. What's the value for k that I want? That's number. I say 6. And what's the number of repeats that I want? I say 8. So I'm going to change that to 8. All right, so I define that. There's no output to look at, so I just move on. All right, it's model building time. So we're going to fit 3 models. The first model is going to predict response rate from all predictors. The second one is going to predict response rate from just this 7 set of predictors here. And the third one's going to predict from those 7 predictors and all two-way interactions between them. Basically, additional variables that are just the product of any 2 particular variables here. All right, so how do we go about doing this? Well, much like in BAS 320, what we do is we give the models a name and then left arrow it to the results of running our model fitting function. Now in BAS 474, we're going to use the train function regardless of what type of model we're looking at. Logistic regression, linear regression, nearest neighbors, support vector machines, etc. The syntax, though, is something you're familiar with. First thing we need to do is specify the formula specifying the model that we want to be fitting, and that's always going to be our y variable, twiddle, and then the model that we want to be looking at. So what predictors are we going to be using? Now, back in the set of R code associated with these notes, I have a big long list of examples showing you how to fit various models using specific predictors, leaving some of them out, adding polynomial terms, adding interactions, etc., etc., etc. You have a lot of flexibility for what models you want to be fitting. One of the more important ones, though, is the twiddle dot shortcut. Just y twiddle dot says predict y from all of the predictors available to us, and we're going to be doing that here. So response rate twiddle dot allows us to predict response rate from the 38 predictor variables that we have available to us in the data. Next argument is what data we're using to fit the model, and this is always going to be data equals train. Make sure that you never fit this to the entirety of the data set because we're just fitting it on the training, and then once we're done, we'll predict on the holdout sample to see how well we did. All right, the third argument is going to say what type of model we want to be fitting. And this is where we specify GLM for linear or logistic regression, just some sort of generalized linear model. And then what we'll do is we'll say, all right, here's how we want that as generalization error to be estimated. TR control equal to fit control, this object that we made up in 1B. Now, once we have that, we're almost done. If you're out working as a business analytics practitioner, this would be sufficient. For this class, we need to make sure to have set seed 474 on the same line as our train function. And the reason why is that the errors are being estimated with k-fold cross-validation, which injects a bit of randomness into the procedure. In order to make sure that we all get the same set of answers, we all need to get the same set of random folds, random assignment, etc. So that's the only way grading is possible, and so we need to make sure that we all had the random number generator set up in the same way so that we all get the same sorts of randomness when we run these commands. So we'll fit model 1, and we'll see that there are a bunch of warnings that come out. We can see what those warnings were. It says something obscure like prediction from a rank deficient fit may be misleading. We're not going to worry about that in 474. If you go on to a master's degree program, you'll learn more about what that means. But for our purposes, we can just ignore it. All right, so we fit model 1. Let's go ahead and reuse some of that code to fit model 2 and 3. Model 2 just wants these 7 predictors, so let's go ahead and copy that and put that into our formula. Now, to make predictions from a particular set of variables, we just say the names of those predictors and separate them by plus signs. So I'm going to copy and replace that little expression with the plus sign so that I quickly can convert that list of variables that I was going to have you guys use with just plus signs here. I'll do that last one manually. So predict response rate from this list of variables. From the training data, of course, using linear regression, estimate that generalization error as required. So we'll fit that model. And now, Model 3 wants us to use this same set of 7 predictors, but then throw in all the interactions between them. Now, it's actually easy enough to specify in R as well. I'm going to put that formula back in there, and if I want to use these 7 predictors along with all two-way interactions, so the predictor homeowner HH times renting HH, homeowner HH times whites, etc., all I got to do is to put those predictors that I want involved in the interactions in parentheses and put something that looks like I'm raising it to the second power. R understands that that means all the interactions. It's not going to put in polynomial terms like homeowner HH squared or anything like that. All right, so let's go ahead and fit Model 3. And then we want to do some exploration. How well are these models doing? What are the estimated generalization errors for each of them? Now, if we type out the name of the model and then look at the environment or the results component, $results, it gives us a bit of insight. Here's the estimated generalization error found with that repeated k-fold cross-validation. And here's the standard deviation associated with that estimate. So we know that the one standard deviation rule says that, okay, any two models that are within one standard deviation of each other in terms of what their error is estimated to be are for all intents and purposes, equivalent. We can choose between them. So rbind provides us a really useful tool to essentially create a data frame of the 3 results components. So I'm going to do Model 1, Model 2, Model 3 results, and here we go. All right, so here's our results. We see that the best performing model, 4.87 estimated generalization error, that's Model 1. The worst, Model 2, slightly higher. Let's talk about if we prefer one versus the other. Part D asks us, is there any compelling reason to prefer one of the models over all the others? Justify your answer. All right, so here's where that one standard deviation rule comes into play. These estimated generalization errors that are popping up here literally just are estimates. It's not like these have been nailed down exactly. This is really just a good guess at what the error is likely to be on brand new data. And the one standard deviation rule says that, all right, any two models whose estimated generalization errors are within one standard deviation of each other are basically equivalent. There's no compelling reason to prefer one versus the other. So let's look at the best performing model. In this case, the root mean squared error was this value. We know that larger values are worse, so let's go one standard deviation above this best value. Any model whose estimated generalization error is below 5.14 is, for all intents and purposes, basically equivalent to this model that we're looking at. And we'll see that all 3 models actually are well within one standard deviation of the lowest, so there isn't any compelling reason to prefer one versus the other. So no, all models are within one standard deviation of the lowest estimated generalization error. So we really have a choice. What choice should we be making? Well, it's up to us. Very often we just go with the model that has the lowest estimated generalization error, predicting response rate from everything. But we'll notice that Model 2 is a lot simpler, only having a few predictors instead of 38. So maybe we would prefer a slightly simpler model. I'm going to go ahead and say, let's just go with the model with the lowest estimated generalization error because, why not? There's no reason to go for a simpler model in this case without any sort of guidance from above, so we'll stick with this one. All right, so Part E asks us to do some further investigation. So we know that all 3 models are acceptable, and so we've selected the model number 1, the one predicting the response rate from all the predictor variables. Now, out of curiosity, let's just see how each of these 3 models are actually performing on the holdout sample to see if we made the right choice. Now, this sort of investigation, this sort of line of curiosity isn't going to lead us to ever change what our final model is. We don't basically tune our models on the holdout sample, but it's really interesting to look at. So first, let's actually just verify that we are generalizing well with Model 1, our final selected model. So how do we make predictions on the holdout sample? Well, I'm going to create a vector called pModel1 that's going to store the predictions on the holdout sample. How do we pull this off? Well, the name of the command is predict. We say the name of the model that we're using to make predictions. We say the name of the data frame. that we want to be using to make those predictions on. So new data equals holdout, and we can run that. If we get that same warning message about rank deficient, we can ignore that. Now, how do we get the typical size of the error made on the holdout sample? Well, we need the root mean squared error on the holdout sample. Let's just calculate this by its definition. So the root mean squared error is interested in looking at the sum of the squared errors on the holdout sample. So let's get the actual values on the holdout sample, subtract off what the model was predicting. That gives us the errors, so minus, plus, sometimes we're above, sometimes we're below. If we square that, that gives us the squared errors for each predicted value in the holdout sample. And the root mean squared error says, all right, well, what is the average squared error? And specifically, what's the square root of that average squared error? That's mean squared error, or root mean squared error for you. So how well do we do? All right, on the holdout sample, brand new set of individuals, mind you, the error is 4.84. Typically, our predictions are off by about 4.84 percentage points. What did we expect? Well, based on the analysis, we expected 4.874. So what we see is that we're actually doing a little bit better on the holdout sample than expected. And that's kind of a rare victory. Typically, our estimated generalization errors are overly optimistic, and the actual generalization error on a holdout sample is a little bit above. Our rough guideline is that as long as the error on the holdout sample isn't more than about 10% or so higher than what was estimated, then we're coming up with a model that generalizes well. It's not overfit, it's not memorizing features unique to the training data. So Model 1 looks to be pretty good. It's generalizing about as well as we expected, and that's always good news. Now the question is, did we make the right choice? Let's go and look at the root mean squared errors for these other models just to satisfy our curiosity. Even if we find out that one of these other models happens to do better on the holdout sample, we're not going to change our mind. Because remember, this holdout sample is used only once, exactly once, just as a sanity check to make sure that our final selected model really is generalizing about as well as we expect. But out of curiosity, let's just see. All right, so it looks like Model 1 actually does perform the best on the holdout sample. Great, so we chose the right model. It looks like Model 2 is the worst, Model 3 is right in the middle. And in this case, that just so happens to be exactly what the estimated generalization errors would lead us to believe. This procedure, this repeated k-fold cross-validation procedure, is pretty legit. It comes up with some pretty good answers here. So that's relatively reassuring. So what we find is that Model 1 predicts the best on the holdout sample. We chose correctly. Remember, even if a different model performs better on the holdout sample than the one we selected, we do not change our minds. Holdout samples just as a sanity check for our final selected model. It can satisfy some additional curiosity as well, but we don't base our final model selection on the holdout sample. And for those of you watching, good job. I'm glad that you are taking the time to see how this works. I guarantee you that this will be an exam question. I will ask you, hey, on the holdout sample, we found a model that performed better than our final selected model. So should we switch to it? The answer is no. We don't use the holdout sample to choose models here. All right, one additional cool thing that the carrot package lets us do is to glimpse how important each predictor is to each model. So the census dataset has a lot of predictor variables, 38 predictor variables. What matters? What doesn't matter? Let's investigate. var imp, when applied to a model, gives us a list of variable importances. These are just numbers from 0 to 100. The actual numbers don't matter at all. It's just the relative sizes. And according to Model 1, it looks like that the median household income in the city in which the census block group is located is the most important predictor, followed very closely by the fraction of households in that census block group that contain related family. Then there's a pretty big drop to the houses with no plumbing, mobile homes, etc., etc. So we could use this to talk about, what variables seem to matter. However, even though this is a really interesting and kind of useful list, it does have a big drawback in that the correlation between the predictors can sometimes give a misleading impression of how important they are. So, to see what I mean by this, let's look at the variable importances from Model 2. And what we'll notice is that we get a very different impression. In Model 2, the fraction of households that are actually owned is the most important predictor, and median household income isn't even on this list at all. So we have, fraction of homeowners, something about age makeup, racial makeup, gender makeup, etc. And these really aren't appearing near the top of the list of Model 1 at all, so why the discrepancy? Well, unfortunately, it's really difficult to figure out which variables are important and not so much if we have a high degree of correlation between predictors here. So for instance, if homeowner household was very, very, very important, if we throw in another correlated predictor with it, then R really can't quite figure out, well, how much importance does that predictor have versus the other correlated predictor. And so here's the issue. If we go and dive into our original data, if we look to see where homeowner household is, and actually look at the data dictionary, we can always bring up the help menu to let us know what all these variables are. We have the issue where homeowner household and renting household are extraordinarily correlated, because this is the fraction of households that own their homes versus renting their homes. And as you can expect, these almost always add up to a number that's very close to 100%. Now, there are some people that are neither renting nor homeowners. These are just kind of freeloading off their friends, just staying at the house. They're counted in the census, but they're not officially paying rent. They're not actually homeowners. And so sometimes the renting plus homeowner fraction doesn't add up to exactly 100%. But it's pretty darn close. If I know what renting household is, homeowner household is basically 100 minus that value. So the upshot is that when we have two very correlated predictors, like the situation right here, it's difficult for R to correctly assign each of those variables the right number for the importances. And so that's why the renting households doesn't actually appear near the top of the list, but it does appear near the top of the list in a much simpler model. So what do we say here? We see that renting household and homeowner household are very correlated. They almost always add up to a number very close to 1. In fact, let's just look at a histogram of homeowner households plus the renting households, not related, we want renting. We see that it's almost always adding up to just about 100%. Sometimes it is exactly adding up to 100%. Sometimes it's a little bit higher than 100%. That's weird. But they're very correlated with one another. So if we find that correlation, we can do it in the training data set. That's fine. It doesn't really matter. This is just an investigation. We're not doing predictions, so we don't have to be too careful. That correlation is minus 0.93, almost as far from 0 as you can get. So there we go. So that's our exploration when doing regression, predicting a numerical response. This example was for linear regression. Question number 2 asks us to do a classification problem. So I'm going to pause it and make a new recording for that. All right, let's do number 2, which will give us some practice in using logistic regression for classification. So the data set that we're going to use is in Reg class again, and it's the EX3 abalone data set. Abalone is a sea creature, kind of like a clam. It has a really shiny, pretty shell, and people eat them over in Asian countries for delicacies. So what we would like to do in this case is to develop a model that can predict whether or not the abalone is old or young based on its physical measurements. It turns out that abalones are kind of like trees, and as they get older, they leave rings in their shells. You can count up the rings to figure out how many years old that abalone is. Who knew? But can we figure out how old the abalone is just by looking at it instead of opening it up and counting its rings? So what I'm going to do is I'm going to take the original data set and run this if-else command. Right now, rings is an integer, and I'm going to classify a abalone as old if it has at least 12 rings, and young if fewer. So this way we'll actually have a classification problem. Rings is a categorical variable now with 2 levels, and so we can use logistic regression to make predictions of young versus old. All right, because we're doing predictive analytics, of course, what we're going to do is to take our data and to randomly split it into the training set and then our holdout sample to use as a sanity check to make sure that our model is generalizing as well as we think it should be. So what I'm going to do is I'm going to go way up to number 1 and just borrow the code that I'd used before. This is the same sort of looking code that I'll be using again and again and again. The only thing I really have to do is change the name of the data that I'm working with. So in this case, it's EX3 abalone. So wherever I see census, I'm going to replace that with EX3 abalone. And in this case, I want 65% training, 35% holdout. So I'm going to change this 0.5 to a 0.65. So set the random number seed, randomly select from all the rows, the integers 1, 2, 3 up to the number of rows, 65% of the size of the number of rows, so that we get a vector train rows, which has all the rows that go in our training data. We define that. We define holdout to be everything but the numbers that appear in that vector of integers for the training rows, and we can confirm that we get the training set that we expect. Oops, so what did I do wrong here? Let's go ahead and run this once again. And there we go. So now we're reproducing the expected first few rows, first few columns of the training set and of the holdout sample. So we're good to go. Now, before we fit a model, we need to say what we're actually measuring about that model and how we're going to estimate that generalization error. And with classification, we have a choice. Do we want to focus on the accuracy of the model, or misclassification rate, or do we want to focus on the AUC of the model? The answer to that question guides us for how we're going to set up that fit control object. So I'm going to go over to the R code associated with this set of notes, and I'm going to find the setting up cross-validation for classification code associated with that slide. And I'm going to copy and paste this into here. So for accuracy, here's how we set up the fit control object. We run train control, and in this case we want repeated k-fold, actually in this case we just want vanilla 10-fold cross-validation. So instead of repeated k-fold cross-validation, method equals CV. How many numbers? What's the value of k? I want 10. In this case, I don't want any repeats, so I'll leave it at that. Now, because we're doing classification and because our model is going to be predicting probabilities, I actually have to tell it that so it doesn't try to do a numerical prediction. So I add class probs equals true to basically turn on the ability to do classification. Now, if I want to fit a model that instead considers the AUC, this command just requires a very small change. In addition to class probs equals true, I would need to add the summary function equals to class summary. So I'm going to leave that here commented out just because it's useful to know that you have to add in that extra argument if you want to be considering the AUC. All right, so we have set up that object. Let's run. There's no output there. That's fine. And what we're going to do is to fit 3 different models. We're going to predict rings, specifically the probability of being young versus old here, because we recoded it, to being old versus young, depending on if the number of rings was at least 12 here. And we're going to be making our models based on all predictors with all two-way interactions, and all predictors that include quadratic terms for length, diameter, etc. So, oops, I didn't mean to predict profit here. I want to be predicting rings, so I'll change that. And how do I set up these models? Well, once again, there's that slide that's very useful for telling you how to set up that formula based on what you want to be predicting from. So let's do this. Model 1 wanted all predictors here. That's easy. That's the twiddle dot shortcut. So I'm going to say model 1 left arrow, and train is going to be the name of my function that I use literally for every predictive model in this course. I specify the formula, rings twiddle. I want to be predicting rings. Twiddle dot says predict it from all the variables that we have available. What data set are we going to use to build the model? It's always train, never the full data set. Then what type of model am I going to be fitting? Well, method equals GLM. That covers both linear and logistic regression. And then how am I estimating the generalization error? TR control equals fit control that I defined up here. And for classification, it's good to add in an additional metric that says, hey, what are we actually measuring about these classification models? Now I'm interested in measuring the accuracy of these models, so I'm going to add metric equals accuracy. If we wanted to consider the AUC instead, you would think it's metric equals AUC, but it's actually metric equals ROC. So I'm going to leave that commented out just as a nice reminder. And let's make sure that we have that set seed on the same line as the train function so that the randomness of the procedure estimating the generalization error with that repeated k-fold cross-validation can be reproduced. We'll all get the same numbers out. So we'll fit model 1, and we'll go ahead and do the same thing with model 2 and 3 here, just switching up the formula. So all predictors with all two-way interactions, well, that's just twiddle dot squared. R understands that it's all individual predictors and then all the interactions between them. New predictors that are just the products of any two particular predictors. And then model 3 says all predictors that include quadratic terms, so length squared, diameter squared, etc. So here I'm actually going to create some extra space because this is going to take a little bit of time. In order to get the squared values of those predictors in the model, well, there's no shortcut for this, unfortunately. I just need to go through and systematically say poly length comma 2. That'll use length and length squared as a predictor. And then we'll also use poly diameter comma 2 plus poly height comma 2 plus poly whole weight comma 2. And you're getting the idea. Sometimes this model specification is somewhat tedious, but it's very flexible. Any model we can think of, we have a way to specify that formula. And so once we've written that out, we got all the spelling correct, let's look back at it. All right, predict rings from length, length squared, diameter, diameter squared, etc., etc. So we'll go ahead and fit model 2. That'll take a little bit longer. Not long really at all. And then the ones with polynomial terms. All right, so how well are these models doing? Well, remember the $ results component of that model tells us the accuracy and then the standard deviation of that accuracy as well. There's that kappa statistic that we talked about in class that we are just going to ignore here. Accuracy is fine for this example. So the best way to compare a bunch of models is to R-bind the results components of those models that we fit together. That way we can easily just scan up and down that list. And so when we R-bind this, what do we see? All right, it looks like model 2, all predictors and all two-way interactions, happens to have the largest accuracy of 78.3%. And then model 3 is second place, followed by model 1 being in last place. All right, so this sanity check here, the accuracy for model 1 should be 0.7766285. Well, I'm not getting that right answer. Let me pause this and figure out why not. All right, mystery solved. When I was giving the hints in the sanity checks, it turns out that I was doing 75% training holdout instead of the 65% like what I instructed here. So if you run into a discrepancy like this on homework, practice problems, etc., always let me know, because very often I end up changing my mind about numbers at the last second, and then I don't quite update all of the code accordingly. So there might be errors like that every now and then, and definitely do check up on that. All right, so we fit model 1 and model 2, model 3. We've looked at the results. And I'm going to go ahead and rerun this code again, making sure that I've split it in 65-25 or 65-35, tenfold cross-validation, boom. And I've updated what that hint is so that it's an accurate hint. All right, so what we still see is that, sure, model 2 does the best, highest accuracy, followed by model 3, then model 1. Now, is there any compelling reason to prefer one of the models over all the others? Well, let's look to see. So here's our model with the highest accuracy. The one standard deviation rule says that any model whose estimated accuracy was within one standard deviation of this value is, for all intents and purposes, equivalent. We can choose between them. So what's our standard deviation? Well, we take that standard deviation associated with that model with the highest accuracy, and we subtract it in this case. worse accuracy or lower values. And so it's saying that, okay, any model whose estimated accuracy is above 75.1% is, for all intents and purposes, equivalent to this model under consideration. And we see in this case that models 1 and 3 well exceed this threshold, so their accuracies are basically equivalent to the accuracy of whichever model happened to have the best estimate in this case. So once again, the answer is no. Model 2 has the highest estimated accuracy, but Model 1 and Model 3 both have accuracies that are within 1 standard deviation. So we could choose between any of these three realistically. Now, without any other reason, I'll probably just go with the model that has the highest estimated accuracy, unless I really prefer simplicity or something like that. So I'll stick with Model 2, which is actually a pretty complex model. All predictors and all two-way interactions is about as complex as you can get, but it looks like the estimated accuracy is the best as well. So we'll go with that. And let's just double check to make sure that it is generalizing about as well as what we expected. So let's go ahead and make predictions on the holdout sample and look to see what the accuracy on the holdout sample turned out to be. So in this case, I'm going to just create a vector P model 2 that's going to contain my predicted classes of all the individuals on the holdout sample. So I'll use the predict function. The model I'm using is model 2. The new data that I'm making predictions on is, of course, the holdout sample. And let's run this. So when we run the predict command, and we're dealing with a logistic regression model, we get out a list of the predicted classes. All right, so how do we get the accuracy on the holdout sample? Well, let's just do this by hand. So the answers here, the actual classes, are in the rings column of the holdout sample. And we know that if we evaluate the logical expression, holdout $rings equals to p.model, the result will be a vector of trues and falses. True when they're the same, falses when they're different. There we go. And the cool thing is about R is that true is the number 1, false is the number 0. So if I look at the mean of this logical expression, this is going to give me the accuracy on the holdout sample, the average or the fraction of observations that were correctly classified. All right, so that's going to be my accuracy on the holdout sample, 80%, not all that bad. Is that about what I expected? Well, once again, we reach this rare instance where the actual accuracy on the holdout sample is actually better than what we expected. Usually these estimates are overly confident over what the error is going to be. In this case, we actually do a bit better on the holdout, so that's a pleasant surprise. No signs of any overfitting because we're actually doing better on the holdout than on the training sample, which is kind of rare. Now, what about these other two models? Now, out of curiosity, let's just see if we pick the right one. Now, we know that we never change the model that we've selected based on the performance on the holdout sample. Holdout's just a sanity check to make sure that the model that we've selected actually is generalizing about as well as what we expected here. But we're so curious. Let's go ahead and look to see how well do these other models do. So model 1, model 3. Let's predict with model 1, model 3, and get the accuracies by hand for models 1 and 3 as well. So model 1, 78%, that 80%, and 80.7%. All right, so what we end up seeing is that model 3, even though its estimated accuracy was a little bit lower than model 2, turns out to do better on the holdout sample. So do we switch to model 3? No, of course not. The holdout sample was just our sanity check for that final model. It just might so happen to be that this particular set of individuals in the holdout sample happen to be just very well predicted by model 3. The upshot is that none of these models look like we have any sort of overfitting because in each of the cases, we actually tend to do better on the holdout sample than on the what our estimates turned out to be, kind of a rare case. So that's a pleasant surprise. So what are we asked here? Comment on which model happens to perform the best in terms of accuracy. Well, model 3 happens to perform the best in terms of accuracy, beating out our selected model 2, but that doesn't change our choice of final model. All right, what about the AUC? So the misclassification rate is probably the most useful metric here, accuracy misclassification rate. So what fraction of these abalones am I getting right? Which fraction am I getting wrong? The AUC is much more interesting of a metric if I'm interested in, say, selecting the individuals that have the highest probability of that class that I'm trying to predict. So if I was interested in, say, selecting the top 500 abalones that have the highest chance of being old, the AUC metric is, a little bit more meaningful than that accuracy or misclassification rate. So let's just see how these three models compare in terms of their AUCs. Now, the AUC is not something that we're going to calculate by hand. We're going to make sure that proc library is loaded. And what we're going to do is we're going to run the ROC command to get the area underneath the ROC curve. Now, the way that ROC works, I'm going to type this out again because it gives me a little reminder. Well, it should give me a reminder. What about down here? Let's bring up the help menu. What's the ordering of the arguments? What do I need to pass to it? So I need to pass to it the response, then the predictor, so the actual values, holdout rings, then the predicted probabilities, not the predicted classes. We actually need probabilities here. So within this function, I'm actually going to reuse this predict command. We'll have to piece this together here. If I add in the additional argument type equals prob, instead of giving me the classes, that's going to give me the predicted probabilities, but I kind of get more than what I wanted. I get a data frame where the first column is the class that comes first alphabetically, and the second column is the column that comes last alphabetically. Now, one thing that we know is that R is always going to build models that predicts the class that comes last alphabetically, so I actually need to feed it this column of predicted probabilities. So what I'm going to do is just to realize that the output of predict is a data frame, and to refer to a particular column of that data frame, I can turn on the column reference with $sign and then the name of the column. So now I just have a vector of predicted probabilities for young, and I can get the AUC. All right, so 0.77, what does that tell us? Well, if the model is to make predictions on a random example of an old abalone and a random example of a young abalone, it looks like there's about a 77% chance that the model would give a higher probability of being young to the abalone that actually is young. So a 77% chance that those two probabilities are ranked correctly. All right, well, how about model 2? How about model 3? How do these compare in terms of AUC? 79 and 79.44. So we actually see that model 3 gives us the best of both worlds. Highest accuracy on the holdout and actually highest AUC on the holdout as well. And that's actually pretty rare. Usually AUC and the accuracy kind of work against each other. Usually the model that does best in terms of accuracy does a little bit worse in AUC. But in this case, we see that model 3 was the clear winner on the holdout. So would we have selected model 3 during training? Well, let's go back and actually set this up and take a look. So this isn't part of the activity. This is just for curiosity here. So what if we were doing AUCs? Well, one thing I know is that that fit control object had to be set up a little bit differently. So let's set it up. Then we also need to change the way that our model is being fit. Don't pay attention to the accuracy, pay attention to the ROC here. So let's fit model 1 and let's fit models 2 and 3 as well. We're just so curious, we want to know what would we have selected. Well, let's actually make sure that set seed is there. So we'll add in metric ROC instead of accuracy. Let's get these three answers out. Now let's rbind the results components of these models to see who would we have selected if we were doing AUC. All right, so we got those models fit. And actually we see that we would have selected model 3 because its estimated area underneath the ROC curve when generalized it's the highest of all three of these. Now you'll notice that they're all still within one standard deviation of each other, so all three are acceptable choices, But if we were selecting based on AUC and just going with the highest value, we would have selected that one. All right, so model 3 also performs best in terms of AUC. And I think that's what we were commenting on. And then finally we say no models show any signs of overfitting because the actual error on the holdout is no more than 10% worse than the estimated error with cross-validation. So overfitting is when the error on the holdout is way worse than what was estimated during cross-validation, and we've guarded against overfitting, it looks like in this case here. So provide a ranked list of variable importances. That's one of the awesome things about the caret package and the train function, is that we can get a glimpse over, hey, what are the most important predictors in terms of the age? And it looks like shell weight by a very clear margin here, getting a score of 100, diameter getting a score of 0. Basically, it doesn't even factor into it at all. It looks like shell weight is kind of the key, the one predictor that gives us the most information. So there we go. There's your tour of doing classification with logistic regression, and hopefully that homework should be no issue for you.